So I think today, uh, I'm going to start now, and it's going to be basic introduction to machine learning. To me, I see it as a kind of whet your appetite, kind of introduction to it. I'm going to talk about how to set up, right? Typical ways of setting up your machine learning environment in Python. And I'm going to talk about linear models, and how to train linear models. I find that if we understand linear models, then we will tend to would understand nonlinear models. The nonlinear models are like the backbone, of machine learning. Probably you've heard of neural networks. Neural networks is a kind of linear model, machine learning nonlinear model. So, but for this evening, I'm going to start with nonlinear models, and I'm hoping that in the next week, the next course, we then transition to nonlinear models. We'll see how we can improve on the performance of our prediction algorithm using nonlinear models. So, because we don't have so much time, what I've done was to do some form of prior presentation. I will probably walk through how to set it up, but I might not complete it, because that might take a couple of minutes. So, but I'll just start, with the setting up. In Python, we typically want to work in an environment, The environment isolates all our packages, So because most times we work on different algorithms, different projects, and it's always a good idea to isolate your environment, and Python makes it easy for us to do using what's called pip, this command pip. And if you type it on your terminal, you might have to install it, but a quick Google search, will tell you how to install pip. And using pip, we can create a new environment. The command for doing that, I'm going to, can you see my screen?
Yep.
Yeah.
Yes, we can.
Okay. So I just wanted to be sure. Um, the command for creating a new virtual environment, it's copied it from another file. It's based on, we create, so let me clear it so that it will be clear. So Python m, slash environment, and then the path. I don't know why. Okay, so the path to the environment, where we want the environment to be located. So the environment is typically a folder. You can think of it as a folder that includes all your packages. So for example, if I wanted to create an environment, what I would do is I would just say Python NV3, this particular folder, and then maybe Civic Tech environment, boom. And then it creates the environment for me. And when I created the environment, when I ls, see when I try to see what's inside this directory, I see that there's a Civic Tech folder here, and that Civic Tech contains my Python binaries and any package that I want to download, from the pip installer. So I can, after creating the environment, I can activate it. I need to activate it. Source Civic Tech being activate. So what you see this, it being, this bracket, telling me that my environment has been activated. So if I pip list tells me all the Python packages I have installed. Right now, just the basic ones that come with a normal Python package, pip and setup tools. In machine learning, there are lots of open source packages that we want to install and use. One very good one that I typically use and is widely used is the matplotlib. Matplotlib is used for plotting our data, like some form of data visualization. So if I wanted to install matplotlib, in this my particular environment, what would happen is I just pip install matplotlib, and then it installs it. It downloads it from the repo and installs it. And I'll give it a second for it to finish. Oh, I got some errors, which is weird. It worked before now, but pip list, it didn't quite install. But I don't know. Okay. It says I need to install Cython, pip install. So many of these packages have some dependencies, but sometimes I tend to have issues when I'm running on Mac. If it is Python, it works okay. If it is on Ubuntu, it tends to work okay. But on Mac, I tend to have issues. But anyway, I've installed Cython now. If I type pip list, we see that Cython is installed in my environment currently. If I deactivate the environment, there are a bunch of packages that we need for this course. So I don't think I'm going to install everything. I'm going to activate an environment that I created, for this particular training. So I'm going to deactivate this particular training, right? And I'm going to source the environment. I called it ML environment. Then I'm going to activate it. So it is activated, as you can see by this bracket. So the IDE, that I typically use for the first stage of development in machine learning is called Jupyter Notebook. Again, if you want to install it, you just type pip install Jupyter Notebook. I think it's already installed for this particular environment. If I type pip list, I would see that I have it already installed, Jupyter. So it's not actually Jupyter Notebook, I'll call it Jupyter. And then it says requirement already satisfied because I've already installed it. Yeah, so that's the idea I tend to use, when I'm starting the process of, machine learning development. First, feel free to stop me to ask me any question, along the line. Yeah. Anyway, so to start the IDE, you just need to type Jupyter Notebook. It's a web-based notebook, and it is going to open on your browser. I'm going to stop sharing. I'm going to open my browser now so that you see the pop-up that came. Let me share screen, Google Chrome. Yep. Can you see? Can you see my screen, please?
Yep. I can.
Okay, awesome. So this is the Jupyter Notebook. It's any file you see having this particular extension IPyNB is telling you is a Jupyter Notebook. So if I open it, I've prepared a couple of examples. The Jupyter Notebook allows us to write code, write markups. So it's like a notebook where you can write your code and you can view all your plots all in one. So it allows for iterative machine learning development. I tend to use it a lot, especially at the beginning, before deployment. So the Jupyter Notebook, I'm just going to, it's like a normal editor. We have the file, you can create a new notebook, Python 3, tell it the language that you want, Python 3, it understands Python 3, So you have all these menus, and then you also have the ability to save, But what it does is it saves it periodically as well, but you could decide to save it manually. So you have all these icons for saving it, and it is divided into cells, This particular, this is cell 1, and then you go to cell 2, I double clicked on it to edit cell 3, and cell 4. So it's like, again, it's a notebook. So today, I think I'm kind of done with the first stage, which is more of how to set up the environment and how to kind of use Jupyter Notebook. I understand perhaps I'm too fast, but that's because of the time constraint. I just want to give like an high-level overview of what the processes will be like from top to bottom, and then hopefully in independent learning, when you go to some form of learning independently, because you would have maybe edit from me, that might be easier to understand. Anyway, so I'm going to talk about today. I'll be talking about supervised learning. It's a class of machine learning. Typically, we have three classes of machine learning. We have what's called supervised learning, we have the unsupervised learning, and we have the reinforcement learning. The supervised learning, what it does, it uses label data. You give it some inputs. You say this is the correct output, and then you're trying to fit in a model to that. So based on the feedback that you get, whether it is wrong or right, the AI or the machine learning algorithm will keep tuning the parameters in such a way to get in such a way as to make sure that our prediction is always correct. So we also have unsupervised learning, which I'm not going to talk about today. That this is more, this does not use labeled data as such. What it does is there is no feedback mechanism. What it does is we are trying to kind of knowledge discovery. We have this bunch of data, and then we are trying to see, are there clusters in the data? For example, something I've used it for in the past was in understanding bladder cancer, So we find that when cells are of a particular feature, they tend to have some exhibit clustering. So we tend to use unsupervised learning in such a scenario to understand our data, like knowledge discovery. And then the third class of reinforcement learning, which is incredibly becoming popular, the third class of machine learning is called reinforcement learning. And what this does is, this is being used across a number of industries. And in this case, there is no label data per se. What we have is a reward system, and it's people, psychologists say it is similar to how humans learn, right? How a baby learns. how babies learn. Um, we know that um, if a baby is trying to walk, it falls down, and then based on this trial and error, the baby eventually learns how to, what kind of control system he should input to to locomote, to move. So this uses trial and error feedback system, right? It's being used to train robots, whereby we say if the robot accomplishes a task, we will reward it accordingly. If it fails any task, we will tend to punish it. And over time, what the robot would tend to learn is to um, accumulate the greatest reward, So that's reinforcement learning. I'm not going to talk about that today, but the good thing is many of the techniques that we learn in supervised learning can be, I think there are similarities, they are all based on similar algorithms. It's easy, once you know one class of machine learning, to quickly pick up maybe a book, an algorithm, study it, and then get familiar with it. So today, just supervised learning. We have is a very simple example, but I think it touches upon all the fundamentals, that you would need, to carry on, understanding machine learning. Today, I have a very simple data, 11 data points. And the idea is we have, given the floor area, I don't know, a use case would be we want to predict what the prices of houses will be, given the floor area. Someone tells you the floor area of the house is this feet meter squared or whatever. Forget about the unit. This is just a data I created on top of my head. And this is the house prices. These are the house prices. And we want to elicit a machine learning model, So the idea of machine learning is we have this data, we train a model on top of it, and then at the end of the day, we don't need the data anymore. We use the model to predict, use it for anything we want to do. Something that Apple does is, and many other phone companies, it has a neural network, it has a machine learning model that is able to predict, classify, in this case, it's called a classification. It's able to classify, are you the owner of the phone or not, right? So it takes in your features, your inputs, and then what at the other end of the spectrum is your output. The output tells you yes or no if you're the owner of the phone, and then you can go in or not. So this is similar approach. We have the house, the floor area, and then we have the price. Given any floor area, any house, and if I know the area, of the house, what would be the price? So in machine learning model, I think the first thing will be understanding our data, right? Doing some form of cleaning, some form of normalization. For this particular data, it's so simple. We probably don't need to do so much cleaning, but I think what is always recommended is, okay, we load the data, I created a function called loading the data, and this data I've kind of inputted it manually, but it could come from anywhere. It could come from a file, it could come from a streaming device, But for now, make it simple. I've just inputted it, myself. And then the first thing I did was to normalize. There are lots of normalization approaches, So, but I normalize is a form of what we call data cleaning, So this particular cell, loading data and cleaning the data, and that's what this particular cell does. To run this particular cell, what I will do is I click on run here. Oh, actually I wanted to run this. I make sure my cursor is there, and then I click on run. It doesn't do anything because this is just a function in Python, right? So I'm just making the Python aware that I have this function called load data. I can then call it from anywhere in my notebook. I like to talk about NumPy. Anybody that works with Python, especially with data science and machine learning, this is an ubiquitous library that you would need, that is typically used, and it allows us to um, use arrays, So import NumPy as NP, and this particular variable, or object is a NumPy array. An array is just a collection of numbers. So again, you would have had to install it, use it like based on in the terminal using pip install NumPy. I think what I'm going to do, I will send you the code, the code for installing all the different dependencies. But typically, our dependencies are, would be in a file. We typically call it requirement.txt, and then we can then call pip install from that file. Pip installs -r requirement.txt, and then it installs all our dependencies for that particular environment and for that particular project. So this function, all it does is it loads the data into the memory, right? And then after loading the data and cleaning the data, what we typically would do is some form of exploratory data analysis. When I mean exploratory, it's just to do some form of plot. The first thing that is always recommended is to plot your data. Does it exhibit linear trends? Does it have non-linearities? So like I said, this particular library was what I was trying to install, pip install matplotlib. It allows us to visualize data. It's incredibly powerful. Currently, I'm just plotting a scatter, but it allows us to do even much more. Animation, 3D plot, histogram. Yeah. So a quick Google search, and then you see. But I have something prepared, and I can send it. At the end of the training. To the Slack channel. Anyway, so again, plot data just plots our data, and I'm, this is the function. Yeah, I'm defining the function, and then I'm calling the function here. So in Python, we have what's called, like in many other programming languages, this is a variable to this particular function, and then this is the default value. It's a Boolean. So I'm saying show, do I want to show the plot or not? If this were to be false, like if I make it to be false, I run this, nothing should show. I think if show false. Well, it did show, which is weird. Okay, I know why. nothing is showing because I don't want it, I don't want to show the plot. And then if I come back here, I set it to true, I am showing the plot. So this is the plot of the data. The data, as you will see, is exhibiting some linear trends, right? We can see that there's a positive correlation between the house price and the floor area. It seems for me that given the floor area, for a larger floor area, that kind of corresponds to an higher, price of house. So plotting this, allowed me to understand, that there are linear trends, and I'm going to start with a linear model. Again, this is a very simple data for a large dimensional data. This data, for now we have only one input, but it could be that we have 1,000 input. It could be that we have 100 input. It could be that we have, you get what I mean, some large number of inputs. So then there are other ways of doing exploratory data analysis. You could do some form of correlation analysis, to see how each variable affects, the output, and then cut the input size down. But lots of approaches that we could do. Anyway, but for this particular one, one input, one output, just plotting it linearly is sufficient. So, and then another exploratory data analysis is just see the distribution of our output. If I look at the distribution of our output, it's plotting the histogram. It informs us of how to select our model, how to define what we'll see later on, the loss function. If it is Gaussian, as it is, this is exhibiting some form of a Gaussian distribution, meaning that it is symmetric. This could be the mean, and then you have this kind of symmetry between the left side of the plot and the right side of the plot. Then the loss function, called the root mean square error, tends to work very well. If it is skewed towards the right or skewed towards the left, then we need to start exploring, some other form of loss functions. So, but for now, again, I'm keeping it simple. Just give you examples of, what a typical machine learning development process, is like. So this is where I think it gets interesting, right? We already see that this model is kind of exhibiting some linearities. And then I'm going to say, I want to start with using a linear model. A linear model is defined as this, it's defined by this mathematical equation. X is what we call the input or the independent variable. In this case, this particular input is the floor area, on the x-axis, on this axis, and y is our house price. X is called the independent variable, y is called the output or the dependent variable. And the idea is we want to say, given any x, can we predict what y is? Given the floor area, can I predict what the house price would be? So this is our model. Our model is defined by this particular equation, y equals to w times x plus b. W is called the weight, b is called the bias. Yeah. So, and to write this in code, I'm just going to write it here. I define a function that takes in the floor area, which is the same as my x value, and then a given parameter value w, a given parameter value or bias, b. And then what it returns? It returns my output. My output is called Y, and that Y is parameter W times floor area plus, parameter B. And that's exactly what I've, that's exactly the same. Ooh, excuse me. That's exactly, the same equation here, that we've written out here. So think about it. So we don't know what W is, we don't know what B is, and that's what we are trying to find out, That's the whole essence of machine learning. Can we find that W and B that gives me the best model? Can we find the W and B that that give me the best model? So for example, I said for just a guesswork, suppose W is true and B is 3 and the floor area is 23, whatever the unit is. I can call this function and then it's going to tell me what the house price is. But you have to remember, this is guesswork. We don't know exactly, what W we want based on this particular data. This is just pure guesswork. And to illustrate how the guesswork works, I'm just going to randomly generate some W's. So I randomly generated some W's using this particular function. I called it analyze linear model. I tell it that I want about 10 plots. I give it well, for now, I'm not using any of this. This will come in handy. Loss function is equals to none, parameters equals to none. So, but when you look at this equation, I'm randomly generating, for 10 plot, how many plot is set to 10, remember? For 10 plots, I'm randomly generating W's and B's. And I want to see how these random W's, how are these random parameters, what kind of model would they give me? And this is what we have here, right? Random parameter generation, and I'm getting this type of result. Some are good, some are bad. I could, the B, I could probably maybe add 5 to it just to see, some. I know why, so. I have to go back to this. It's not showing the data point, and I wanted to show the data point. Okay, let's go back to that particular. Yeah, so for random generation of W's, I run it again, I can run it multiple times to get some other random weight. What we are seeing is that some is good, some are bad, First and foremost, this model is not good. The pink one, the blue one is not good, it has too much slope. Perhaps the one that is closest will be this particular one. So these are randomly generated weights and biases, randomly generated parameters. But we might be lucky and then we'll find a good one. But this is just a linear model. For nonlinear models, it becomes even more complicated, to generate to guess what the weight should be, For linear models, it seems, that we could, but for nonlinear data and highly dimensional data, yeah, this is not feasible. So what machine learning allows us to do is it allows us to systematically find the parameters that would give the best weight. It allows us to systematically find the parameters that will give us the minimum, that allows the weight. It allows us to find those parameters that allows the plot fit the data perfectly. And that's what, machine learning does. Whether linear or nonlinear, That is the same principle, you know. So, and to do that, there are three steps we need to follow. The first is we need to define what our loss function is. You know, we need to define what our loss function is. Imagine a scenario where for this particular pink one, right? Let me see if I can zoom in a bit. For this pink one here, the blue dotted line is what our data is. But the prediction for the pink one, even it is negative, right? It is saying negative house price, which is not even realistic. Or for this particular blue one, blue color, it says the house price is about 30, but for a floor area of about 30, then the house price is about 30, but that's not what we get. We are getting about maybe, you know, if I go back to look at the data again, for house price of about 21. Oh, but this is normalized, by the way. For house price of about, for house floor area of about 30, we are getting about maybe 4. You know, the value is 4, maybe whatever 4 is. I'm not putting any unit to it. So 30 is a bit too high. Yeah, well, not a bit too high. It is greatly too high. The value is 4 here, but this particular model is predicting 30. So there's a difference. So that difference, you know, 30 minus 4 is what we call my error. So my loss function is just the aggregation of these errors, you know, across the data points. So I define a loss function. I say my loss function is whatever I predict minus the real value of data that I get. But because I don't, you know, to prevent negative, you know, to make sure, you know, whether negative or positive, it works, I square it. You know, this is what we call by mean square error, you know, or squared error. So this is the error. What we have here inside is our error, and then we are squaring it, you know. So we define this loss function. So what we want to do is we want to find that particular parameters, those parameters that give us the least error. So for example, this particular maybe gray one would expect it to have lesser error than this particular blue one here, and you'll see. So I defined a loss function, you know, or an error function, as some people call it. So what we are seeing here is for this, again, I'm generating random weights and I'm analyzing what the loss or the error is. I'm saying for this particular weight, you know, for weight 0.33, bias minus 0.50, the loss is 4, you know. If I run it again, this particular weight is very bad, you know. The other one was 4. This one has much larger error. I run it again. This one has much, another, you know, an increasing error. I run it again, you know, even worse, you know. So the loss function tells us how good a model is, you know, how good the weights are, you know. I run it again, yeah, it's just bad, you know, everything is bad, you know. So after I've defined the loss function, the next step would be we use some form of we use maths basically to improve on the weight. So the idea is, imagine, so the loss function is, like I said, it's a function, is for a linear model is quadratic. Think about it as a quadratic loss. Think about it as a valley, right? So for and you're standing maybe at the edge of the valley that represents a particular weight. But you want to go down the valley, you know. The bottom of the valley represents, you know, the least amount of error. So what this what we call the gradient descent algorithm. What it helps us to do, it helps us to find how should we improve upon this parameter that we have, you know. For example, if I have this parameter, I start with this parameter minus 0.1, 1.01 and minus 0.95. The algorithm tells us, how can we improve upon this? How can we go down the valley to get even lesser error, you know? And to do that, we need to, I've tried to keep the maths to be at as minimum as possible, but I think this is understandable. So what the gradient does is it helps us to go downhill on the loss function to improve, to make sure that at every training step, I'm getting lesser and lesser error. And this is this the formula for doing that. We use what we calculus, you know, we find the derivatives of the loss function with respect to the parameter. For now, I'm using W, you know, the weight, but it has to be done across all the parameters. For a linear model, we have two parameters, the weight and the bias. For a nonlinear model, we could have, you know, there are some neural networks now that we have a billion parameters. So it can get complicated easily. But for a linear model, just two parameters. But everything still boils down to this particular equation here, you know. How do we go down here? How do we use this particular derivative? Excuse me. How do we use this derivative to go down here? So from calculus, we use this formula. This formula tells us what direction we need to go into, and based on the product rule of basic calculus, because this loss function is has an f component in it. F is our error, you know. F is our error, the predicted house price minus the real house price, you know. And then the predicted house price, F can then be written as the floor area, because this keep doing that. The predicted house price is our linear model defined here, you know, minus the real house price, you know. So this error for a particular data point is just the input, which is the floor area, times the weight of the linear model times B. It is this W and B that we are trying to find. We have this already. We have the floor area, we have the house price, you know, for that particular floor area based on the data that I present. So we are trying to find W and B. To find the derivative of, you know, we need to find dl and df and df dw. To find the ldf, based on the square loss function, you know, this is f squared, you know, the ldf, you know, if for the finding derivative of f squared is 2f, you know. And if you're finding derivative of df dw, this is f, this is f, and f is given by floor area times w plus b minus house price. The f dot dw is just typically just, you know, because these are constants, they become 0, and then if you're finding derivative of this cancels out, you know, and it cancels out, and then what you have left is our floor area. If I wanted to find derivative with respect to b, because this has no b term, you know, it becomes 0. This has no b term, it becomes 0. The f db, you know, it has a b term, is a constant, it becomes 1, right? Yeah, it's these are calculus, you know, stuff. But it might need a bit of brushing up, you know, the calculus, but it doesn't get even more complicated than this, you know, even for highly nonlinear model. If you could maybe spend some time to understand this, it's for highly nonlinear model, it's still the same principle. We are finding these derivatives, from basic calculus. And then we code it, we have what the derivatives are, the grad function, this particular grad function is what I've written here. It takes in the floor area, takes in the house prices, takes in the predicted house prices, the parameter W, the parameter B. So it tells us what the grad is, what step we need to make to improve upon the loss, given these particular W's, these particular parameters and this other input. So this function here is the same as this first function, right? Is this same here? This function here, the model, the W is the same as this equation here. This function here is the same as this equation here. It just returns 1. And then remember that we need to get the LDW, we need to multiply each of the parameters, the FDW times the LDF. The LDF is 2F, and the LDW is our floor area. So the loss dW, which is this particular equation here, the LDW, is just whatever comes out of this one here, the loss dP, this particular equation, which is our 2 times F times the floor area, Yeah. So, and the model dW returns the floor area, So, and yes, we have, in the second step, we derive the gradient, The gradient is just like I say, I'm reiterating it because I think it's important. It's just a way to tell us how do we improve upon this particular model at this particular time step. I have a W and L and W and B. What can I do, to improve upon it to get a lesser loss? And when I've calculated the LDW and the LDB, the way to improve upon our weight and our bias is just to subtract, because we are going downhill, So, and the alpha is what we call the learning rate. It controls how much step we want to go downhill. If it is too large, it could be that we don't actually go downhill, we climb over the valley instead. So we need to do some form of what we call tuning, So the alpha controls the level of how we want to go downhill. And so what we do is we run these multiple time steps, what we call the number of epochs. For example, maybe 10 times. We start at a particular parameter, what we call the initial parameter, and then at the first iteration, we calculate what our DLDW is, and then we improve upon the particular weight. We calculate what our DLDB is, and we improve upon that particular bias. And that's exactly what this particular equation does, function does. What this function does, epoch, number of epochs. For each epoch, we take what the parameters is, right? And then we calculate the grad, based on this equation that, we have up here. The grad function is called here, and then that gives us what the grad is, and then we improve upon the parameters. So params equals to params minus the learning rate times the grad. Grad in this case is a vector, the params is a vector because I have combined both the W's and the B's together into a 2x1 array. So, and then we run it, we run this function, we run the training loop. I'm running for 20 epochs. So after running it, what we are seeing is at the first epoch, our loss is 447, which is very large, right? And the AI is able, the machine learning is able to, algorithm is able to use these equations to kind of, like I say, go downhill, right? It improves upon the model. It improves on the parameters, in such a way that at the second epoch, the loss is now smaller. At the third epoch, again, it takes the parameters that we have gotten in the second epoch, it tries to improve upon it to get even lesser loss. And then you do that over and over again. And at the end of the day, the loss comes down to 5.0, We could increase the number of epoch and to even get better results, or lots of tuning that we could do. For example, I could play with the learning rate. The learning rate, like I said, tells us what steps, the level of step that we want to take. If it is too large, if I find it too large, we'll find that it might not converge. So it requires a bit of tuning, back and forth. And that's why I particularly like the Jupyter Notebook. It allows me to quickly, visualize, how the algorithms are doing. And at the end of the day, we have a systematic way of getting the parameters that we want. Now, it becomes tricky. If this were to be, I think for next week, this model is going to be improved upon. This particular model is going to be improved upon on this particular data. And then we are going to see how a linear model would not perform very well on the nonlinear data, right? Imagine that this particular x-axis, there's an increase, and then there's a tapering down, or perhaps there's a decrease, it becomes like a plateau, and then there's a decrease. What this linear model will keep going up, and that's where a nonlinear, model can help us improve on the performance of the algorithm. So next week, I think I'm out of time. For next week, the plan is that we don't have to do all this mathematics by ourselves. We have open source packages that does that for us. PyTorch, it's widely used, across the industry, even for very safety critical systems. So we don't need to do all these things by hand. The reason why I kind of, explained it is to give like an intuition of how this is done. But we don't need to do it anymore, especially for highly nonlinear models. This can become quite messy. So we have open source packages that can do these things for us already. And for next week, I'm going to be introducing, PyTorch, especially, and how PyTorch can be used for linear models and how we can use it for nonlinear models. And it's just so easy. It's just a few lines of code, to do that. And yeah. I hope I wasn't too fast.
My brain is leaking.
Brain damage.
I know it's difficult. Oh man, it's lots of information.
It is, but don't take that as a bad thing. Like that was Very interesting. Brings me back to my university days, and you have that one teacher who's passionate about their work and they love teaching it. By God, they sometimes just go right over your head.
Yeah. Um, yeah. So it's quite, lots of things to cover, lots of details I've skipped over, but I think it might be more interesting next week. Like I say, I'm doing some calculus, which for machine learning currently, I don't think we need to do it. Just understand how to use the packages, the PyTorch module, and then you're good. So I'm hoping that next week it will be more. It will be easier because it will just be pure code. No maths this time.
Once I saw that calculus, I cringed a little.
Yeah.
Yeah.
But in seriousness, I appreciate this. This was awesome.
This is really good, and it's a good lead in, a good introduction to what hopefully we'll be doing with Torch. This is really good.
Yeah. So I will share some of the materials on the Slack channel, and then maybe you can play with it in your spare time.
Mm-hmm.
Yeah. So yeah.
Excellent.
Well, and do you have any question at all?
I don't even think I understand enough to ask the questions.
Oh, okay.
Sayo, maybe you could have some recommended learning links or stuff like that, maybe.
Awesome. Yeah. Okay. I can.
I should be honest, it sounds like I'm listening to my husband.
I have just one question.
Okay.
Can we use Google Colab instead of installing all the packages?
Of course you can, Google Colab, it's online. You don't have to do it locally, It's similar to Jupyter Notebook, so you don't have to install it basically. I think the short answer is yes, you can. And it's the easier approach.
Okay. Yeah. Thank you.
Yeah.
Awesome. Thanks, Sayo.
Thanks. Thanks, everyone.